Just give it a moment. I'm going to join here. Okay. Right. As people are kind of joining in here, I will guess I'll go ahead and start things up. Oops. It's bugging out on me a little bit here. Okay, can everyone see my screen okay here? Or sorry, can you see my screen okay? I just wanted to double check. Okay, great. Okay, hello everyone. Thank you for joining us and welcome to today's Polariton webinar. I'm Garrett Wiesahan, a graduate student at UC San Diego, and today I will be the host for the webinar. So here is the schedule for the upcoming talks for 2021. Today is Professor Ritesh Agarwal. Our webinars are held every Wednesday at 9 a.m. Pacific Standard Time. Registration for each webinar can be made through this link right here. We provide in all of our email reminders. Registration is required for each week's webinar, and you can also find them posted on the social media here on Twitter and Facebook. We do have a Polariton chemistry online community on Facebook here, which allows everyone to share papers and post announcements. You can search it by name here, this Polariton chemistry online community. Additionally, we upload the recording of these Polariton chemistry webinars to our YouTube channel in case you missed the talk. You can search on YouTube also by the name here and find us, and also make sure that you subscribe to help support the channel here. Finally, I would like to introduce the mechanisms for this webinar in case this is your first time joining us. During the talk, attendees are all muted. If you have questions, you can raise your hand, and I will interrupt the speaker at an appropriate time and enable your audio to ask these questions. Additionally, you can type your comments or ideas using the chat function here, and you can share these questions with everyone. Finally, you have a Q&A option where you can type questions and they will be addressed at the end of the talk. And for questions that are not answered due to the webinar time limit, we will collect and send them to the speaker after the talk, and they will be answered on social media or by however appropriate means to continue the discussion after the presentation. And with that out of the way, I would like to move on to today's webinar here. So it's our pleasure to have Professor Ritesh Agarwal from the University of Pennsylvania as today's speaker. Professor Agarwal completed his undergraduate studies in chemistry at the Indian Institute of Technology, Kanpur in 1996. In 1997, he completed his master's degree from the University of Chicago and in 2001 was awarded his PhD from UC Berkeley. At Harvard University, he was a postdoctoral fellow working with Professor Charles Lieber, studying the optical and photonic properties of semiconductor nanowires. His work there led to the development of electrically driven single nanowire lasers and avalanche photodiodes. And starting in 2005, Professor Agarwal began his time as a professor in the Department of Material Science and Engineering at the University of Pennsylvania, where he continues to lead the way in research in nanoscale photonics and phase change. He has been the recipient of the NSF Career Award in 2007. In 2010, the NIH Director's New Innovator Award and the SPIE Symposium Nanoengineering Pioneer Award in 2014. His research interests are on understanding light-matter interactions at the nanoscale using 1- and 2-dimensional semiconductors and plasmonic nanocavities. And currently his research has focused on topological photonics and their ability to serve as a basis for the development of robust optical devices and circuits. Today he will give us a talk entitled Helical Topological Polaritons. And without further ado, I would like to welcome Professor Ritesh Agarwal. And you may now share your screen and begin your discussion. Thank you.
Just give me a second. So are you able to see my screen?
Yes, perfectly.
Well, thank you. Thanks for the introduction. And thank you all for joining this session, this discussion. But first, I'd like to thank the organizers for doing a great job in doing these weekly seminars and keeping everyone engaged and busy while we went through a crisis. But we sort of coming out of the crisis. I mean, 2 days back on Monday, I was able to get my first shot of the Pfizer vaccine. So things are looking up. So hopefully we'll be all able to meet and discuss in person. Until that happens, we have to, as the organizers, mission is keep everything moving. So with that spirit, I'd like to discuss some of our recent work on trying to create, if you may, a new phase of optical matter, which I'll explain in detail, which we call helical topological polaritons. And so at the core of this is, again, is our efforts, or the community's efforts towards engineering and understanding how light interacts with matter, and then looking at the microscopics, and from what we understand, taking it, endowing it with new properties. And the new properties that I'll discuss in the latter half of my talk would be on utilizing the geometry of the system, in the momentum space geometry of the system, combined with real space geometry, which leads us to engineer these properties to create these robust polaritons, which can propagate with spin-dependent transport in our devices. Okay. So before I start, I'd like to thank all my wonderful students and postdocs who've contributed to this work. So this work, our efforts in two-dimensional materials was initiated by Bamsu, who's a postdoc in my group, and Juhi Park, along with Wenjing. And then the topological aspect of this work was initiated by Wenjing. I think she is in Peking University and is attending the webinar, along with Zurun, Yuhui, and Minsu Huang, the funding agencies which have funded all this work. So we have to be very grateful that during this crisis, they were still able to fund the work and not shut down the lab. All right, so before I get into the topological aspects of our polaritons that we are trying to create, just to, I'd like to, first 10, 15 minutes, I'd like to talk about how we got to this problem. And, thanks to this community for bringing these very interesting problems to the front, and which got us motivated. So when you have an emitter, a quantum system, let's say it's a two-level system, and when it couples to the optical field, and this is something this community knows very well, but just only for completeness, then the interactions can be broadly classified as under the weak coupling or the strong coupling regime. So in the weak coupling regime, the coupling between the two, let's say oscillators, the emitter, and the optical field, if the coupling is weaker than any of the smaller than any of the line widths of the two systems, then we don't really change the eigenstates of the system. But of course, you change the density of states by creating, let's say, a cavity or any field around the emitter. And a simple, time-dependent first-order time perturbation theory is enough to, to understand the system. And this leads to very interesting effects, such as, a Purcell effect, where the emission or absorption rate can be enhanced, and lasing, simple photonic lasing. And then the other extreme, if the coupling strength is much larger than any of the decay channels of the system, then the system can oscillate coherently between the two oscillators. And in that case, the perturbative approach doesn't work, and one has to create the new eigenstates of the system by hybridizing these two modes. And we create what are called polaritons. And the interesting thing about polaritons, and that's why there's so much interest, is, it, in principle, although it is challenging, but in principle, and people have done great amount of work to show that one can utilize the important aspects of both the photon or light and matter, the long, the coherence, the long propagation distance of the optical mode of light, and interparticle interactions and nonlinearity of the material. Whatever excitation, could be vibrational, excitonic, whatever that excitation that couples to the optical field is. So many years back, we started to make these optical cavities by combining semiconductors in different geometries with intrinsic geometry of the system, or with external plasmonic cavities. And what we found was, if we took a one-dimensional or quasi-one-dimensional nanowire, let's say made of cadmium sulfide, a direct bandgap semiconductor, and if we engineered a conformal optical plasmonic cavity, then there's, at certain length scales, we could create very strong plasmonic modes along the circumference of the cavity, leading to extremely large Purcell factor enhancements of the order of 1,000. And these enhancements were so large that most of the emission from the excited state came from what we call hot excitons. So they were violating in the molecular spectroscopy. There's this idea of Kasha's rule. So they were violating the Kasha's rule that the emission was not taking place from the lowest excited state, but even before the system could thermalize in the excited state, the system was forced to emit. And so after demonstrating that, we applied this idea to a material like silicon, which does not emit light in the bulk regime, and then we were able to make silicon emit light with internal quantum efficiency of the order of 1%. So this shows, by engineering light matter interaction, even in the weak coupling regime, one can get very interesting properties. And so we did quite a bit of work on that. But since the focus here is polaritons, and you all know what polaritons are, it's a hybridized state of light and matter, and one can get these interesting dispersions in an extended system. You solve this simple 2x2 Hamiltonian, and and extract the states as a function of k, and the splitting at this is a measure of light matter interaction strength. Okay, so again, initially our work was on nanowires. So you can imagine nanowires with diameters of the order of 100 or 200 nanometers. So very strong confinement along the cross section, but extended along the third dimension. And we showed when the nanowires are large, the size of the building, all the way down to the light matter coupling strength matched that of the bulk material. But if we reduce the size of the nanowire below a certain size, which again depends on the polaritonic properties of the system, that the system suddenly transitioned from a three-dimensional polaritonic regime to sort of one-dimensional polaritonic regime, where the light matter coupling strength was a very strong function of the size. So by doing this size-dependent engineering, we basically showed that that they can tune the properties of this polariton, and because of these enhanced nonlinearities that one can get, we were able to make a polariton, all optical polariton switch by scattering the polaritons in this one-dimensional channel. And recently, with collaboration with my ex-postdoc, who's a faculty member in Korea, we show that one can get polariton lasing at room temperature in these multi-quantum well one-dimensional structures. So I won't have time to talk about these things, but you can always look up these papers. So there's a lot of space to play, and with geometry, which is nanowires, and also by creating the different kinds of cavities. So around 5 or 6 years back, not time flies, so 6 years back, maybe 5 years back, we started to, there's a lot of activity in what are called these two-dimensional systems, which are basically, most of the focus is on these layered materials where you can peel off the material starting with graphene and then extend it to semiconductors like transition metal dichalcogenides. So you can create these planar materials which are van der Waals stacks. So you can go down to a monolayer, and in a system like MOS2 or similar systems, it was very nicely shown that these materials undergo a transition in the sense of when it's a multi-layer system, it's an indirect bandgap material. But if you thin it down to a monolayer, it becomes a direct bandgap material. And this, of course, has to do with orbital interactions in the z direction, which can shift this energy of the bands at the gamma point or the k point. So these materials are very interesting because when you thin it down to few layers, then the excitons are not adequately screened. Because the electron-hole interaction is not screened, they can have very large binding energies of the order of few hundred MeVs. Claims are made of the order of 1 electron volts, but let's to be on the safe side, few hundred electron volts. And when you go down to a monolayer, in the monolayer limit, you have time reversal symmetry because these are non-magnetic systems, if they're non-magnetic systems. But inversion symmetry is broken. So the two values at k and k prime, and this becomes important for some part of my talk. One can have transitions. One can address these values uniquely, otherwise degenerate values at k and k prime via circularly polarized light. So if you have one circular polarization, you excite carriers only in one valley, and the other opposite circular polarization excites carriers in the other valley, leading to what is called valleytronics. So this is an important aspect, and for this talk, another aspect is because the carriers are not adequately screened, there is long-range interaction, many body interactions, which can occur over length scales of the order of many orders of magnitude more than any other semiconducting material, which is not a monolayer. Again, because of inadequate screening. And if you inject any carrier or extract any carrier from the system, one can change the physics, or interaction or the dynamics of the exciton recombination, and also lead to what is people have shown the formation of trions even at room temperature or close to room temperature. The trions happen in any semiconductor material, but it's very hard to observe them because the binding energy is very weak. But again, because of inadequate screening, the binding energy of trions in these two-dimensional materials is comparable to room temperature. So one can see this signature of trions in the optical spectrum. So again, once you have a two-dimensional material, how do you define a cavity? So there are dielectric cavities which have and people have done a lot of very interesting work. But our interest a few years back was in plasmonics. But you can't sandwich this material between two thick layers of metals because you have to get light in and you have to get light out. And our interest was making large area devices. So instead of putting a single nanoparticle and confine light at that length scale, we wanted to do something on a larger scale. So then through trials and error and because of this vast literature available on these lattices of plasmonic particles, we were able to create these crystals of plasmons. So at individual particle, you have these localized plasmons, and collectively over a large scale of this lattice, one can have a lattice mode, which is nothing but in-plane diffraction mode of these plasmons. And by doing this, one can engineer the optical modes of this plasmonic lattice. and it couples very nicely to the underlying two-dimensional system. And then the idea was to study these interactions. So here, this is just an image, dark field image of just the plasmonic crystals. And by changing the lattice parameters or the size of the individual nanoparticles, one can get different colors scattered from these things. These are structural colors, as you all can guess. Okay. So our first effort was, this was some time back. So bow ties, we created an array of bow ties where the idea was between the two apexes of these, of these triangles, one can confine fields very strongly. And if you have a lattice, then one can engineer a lattice mode. And by engineering this lattice mode, what happens is, one can increase the quality factor of the plasmonic modes. And by doing so, our first efforts, led to very strong enhancement of the emission and the Raman scattering via the Purcell effect. So we showed this, and by tuning the lattice modes, again, via pure geometrical effects, we were able to tune the emission spectrum and also show blue emission, which means unthermalized emission from these two-dimensional materials. So you can see this blue tail when the lattice mode is tuned to the high frequency side. So that means the Purcell factor is pretty large, not as large as 1,000 because these are not the same structures as those curved geometries, but still large enough to compete to some extent with the thermalized emission. Then, as we improved our designs, and and the material improved, and the and our fabrication improved, my students started to report something very interesting. So if the differential reflectance spectrum that you see here, if you just have the two-dimensional material, you have these two very nice excitonic modes or excitons. And this blue curve is just the plasmonic cavity. So if we start to tune one of these plasmonic modes close and start, and make it, bring it close to resonance to, let's say, the A exciton, this is the hybrid system. So now we fabricate these modes, these plasmonic crystals on top of the MOS2 layer. Clearly, we can started to see this splitting in this excitonic spectrum. And these are asymmetric modes. So, but clearly, the line shapes were changing. So this was telling us that we are, and this got me excited. And this was published in 2015. So this was a long time back. That clearly a two-dimensional material, which and combined with a plasmonic cavity, which has all the issues of a plasmonic cavity, strong damping, still one can start to change the line shapes of the material. Okay, so this was not strong coupling, but it was approaching strong coupling. So this is basically not, the term is Fano resonance, where you have two-level system coming from the exciton, let's say, dipole coupled to a continuum of plasmons. So you have two initial states and two final states, direct excitation of the exciton or via the plasmons, and then there's interference between these two pathways, leading to this effect. So this set up the agenda for which we're still following until today, and that is, can we now push the system to strong coupling limits, where we can create exciton plasmon polaritons in these systems? And the answer is yes. Again, by improving the geometry instead of going with the bow ties, because bow ties are can have very large inhomogeneous broadening, because these are triangles. So at the apexes, in the fabrication, you're going to have problems. Silver is a polycrystalline material, so you'll have rounding at the edges, and you can't control the rounding exactly over the large array. But if you have a disk, a nano disk, then it's sort of it's better. So we showed inhomogeneous broadening can be reduced, and again, and then once we improved all these things, we were clearly able to show that one can create polaritons in these exciton plasmon polaritons, and by tuning the geometry, either the diameter of these individual particles or the lattice constants, one can tune the surface plasmon on lattice resonances, or detune them or tune them with respect to excitonic resonances, and create these polaritons. And so now coming back to uniqueness of these two-dimensional materials. So one unique aspect of these 2D materials, as I mentioned, is because of this inadequate screening, there's long-range interaction between excitons or between charges that you can inject or extract from the cavity. So
Sorry, Professor.
yeah,
We had one question
sure,
from Hoel here, so I'll allow him to talk.
sure.
Hi, I just have a very simple question to ask you in this geometry. Is there also MOS2 in between the nanoparticle, the plasmonic nanoparticles, or just on top of each of the nanoparticles?
So yeah, so we you mean in this transistor in general, what we have is a silicon oxide, and then the two-dimensional material, and then the plasmonic cavity is patterned on top of the 2D material.
So there is 2D material in between the nanoparticles. So like in those spaces between the nanoparticles, there is also MOS2.
What do you mean in between? So it's a 2D extended system,
Okay.
and then on top we pattern these plasmonic particles.
Yeah. Okay. So I think that answers my question.
Okay.
Thank you.
And the reason why we don't put these 2D materials on top of the pre-patterned lattice is because of the strain effects. Because you can create large strains, and that changes the resonances of these 2D materials. So this is the reason why we pattern on top. Okay.
Sure. Thank you. Yeah.
All right. So coming back to can we? The question we asked was, we can create polaritons with these plasmonic structures. These are open structures. So it's easy, or relatively easy to integrate this with the field effect transistor geometry, where we can inject or extract carriers. So can we tune the electron exciton plasmon coupling strength by these electrostatic gating of the material of this device? So so this is the schematic of the device. So silicon oxide, heavily doped backgate. So where you can apply bias and gate the device. It's not the most optimum transistor device, but that our idea was not to compete with Intel and other companies, just to extract carriers or inject carriers in the system. Okay, so this is how the device looks from the top. Okay, so yes, indeed. So at 0 gate voltage, we saw this level repulsion at the A exciton region, and then as we injected carriers, then we started to see this weakening of this A exciton level repulsion, and then some perturbation in the line shapes at the trion, because we're injecting carriers, so it starts to form trions in the system. And as we inject more and more carriers at larger gate voltages, the A exciton level repulsion simply disappeared, and we started to see more perturbations in the line shape of the at the trion resonance. So I can not going into the details. So if you plot this this behavior as so we can extract coupling strengths by fitting this to this multi-exciton model as a function of gate voltage. So at 0 gate voltage, 0 doesn't mean no extra charge, because these are generally intrinsically doped materials, but 0 means no external voltage applied. So we have reasonably large, a very strong coupling with the free excitons, and almost nothing with the trions. And as we inject carriers, you can see the coupling strength decreases in the free exciton, and for the trion it increases. So this basically gives us a handle to control, in these unique geometries, light matter coupling strength in these systems. And then one last thing before I move to the polariton to topological case. So what Wenjing did was also show that instead of, if you have a monolayer, and if you go to bilayer or trilayer, since the physical spacing between the two layers is very small, so when you go from monolayer to trilayer, all we are doing is we are packing more excitons, or the exciton density increases within the plasmonic mode. So what she saw was very interesting. So if you have these multi-layer system, we only try to trilayer, and then we pattern this plasmonic lattice. Then as we go from monolayer to trilayer, a new mode emerged. This dark line, in our reflectance geometry, this means there's a resonance there. So there's a very strong, almost non-dispersive mode that emerges, followed by this bright region, which means no excitations are allowed in the system. So we call this a polariton gap. Yeah. And then the upper polariton branch. And then from here, if we extract the coupling strength, it's of the order of 100 or 110 MeV. It's a very strong coupling strength. And after a lot of simulations and calculations and a lot of experiments, we basically showed that the emergence of the new mode is because of very strong extern interactions mediated by this periodic plasmonic field. So again, this is another handle in these two-dimensional materials to reach these very interesting regimes where interparticle interactions can shape the spectroscopy and the response of the system. All right, so the formation of this polariton band gap that I talked about led to some very interesting ideas, which as of now have failed, but forced us into this topological other routes of creating this topological modes in the system. So we were very excited because again it will become clear as we go forward. So this is like a preview. When we create this polaritonic gap, and let's say if we have a hexagonal lattice instead of the square lattice, and one can have these Dirac dispersion in these honeycomb structures. This is the and once coupled with this multi-layer system, we saw this band gap opening and formation of these curved parabolic bands with some mass. And then by changing the lattice parameters, which I'll talk about, one can basically invert the bands and create topological structures. So this was the idea to create topological polaritons in these heavily interacting systems. But plasmonics are plasmons are heavily damped, so we had to kind of give up this approach. Although we are still now coming back to this problem as more advances are made in the materials and the geometry. But this led to can we create or endow topological properties in these systems? So again, this is a polaritonic community. So just if you're not aware of what topology means, or so I'll just give a very brief overview. I'm a learner of this. I'm pretty much new in this field, so I'm learning as I speak. So if I can get it, all of you should be able to get it. So the idea of topology. So this is something very interesting. So Gamow, the famous physicist Gamow, once remarked in 1950s or 60s that mathematics will always remain an integral part of physics, and almost all branches of math will impact physics except number theory and topology. Yeah. So, and that changed dramatically within 2 decades of his statement. And the experiment that actually changed this whole thing and introduced the idea of topology in physics was this quantum Hall effect. So in quantum Hall effect, just like the Hall effect, you have a two-dimensional in semiconductors. You have a two-dimensional electron gas, and you basically apply put electrodes and you apply a very strong magnetic field, and then you measure transverse current. So you apply electric field in one direction and measure transport of in the orthogonal directions of the transverse direction. And what was found was these conductance plateaus in the transverse direction. So, and what was surprising was these conductance plateaus were quantized very, very precisely. It was so precise that the quality of the system, unless of course it was too dirty or the disorder was very, very strong, it didn't matter. And this was very surprising because in transport physics, if you change the disorder, if you change the resistance of the sample slightly, it shows up. But these conductance plateaus did not pretty much care. Of course, you can always destroy the system and then you won't have a good electron gas, and scattering and all will destroy you completely. But within the within reasonable limits, this was very, very strange. Yeah. So this again, a lot of Nobel Prizes and huge amount of work has is going on in this field, continuing till today. But what came out from all this was there must be something else that is determining the properties of the system, not local properties, but what are called global properties of the system. And this led to the idea of topology in physics and condensed matter systems. And these topological systems are typically defined or described by these global parameters, not local, what the electron samples typically, but global phase, global invariance, either called the Zach phase, winding number, Chern number, Z2, so on and so forth. And also, since this transverse current, these conductance plateaus, when these occurs, the transport occurs along the edge of the sample. but the edge properties are determined by the bulk. So this led to a very important idea that's the bulk edge correspondence in these condensed matter systems. So these are quantum Hall systems where you apply a very strong magnetic field and you break the time reversal symmetry. And then a big breakthrough occurred at Penn, and these are my two distinguished colleagues in physics, Charlie Kane and Jean Meillet, who basically realized that one can also have topological properties in the system without applying a strong magnetic field. And this effect that they discovered is called the quantum spin Hall effect. So again, just for the sake of completeness, in the geometrical spaces can be defined from the topological aspect by what is called the genus of the system. And to give a simple example, not the only way, but one particular example is count the number of holes in the system. So like a sphere has 0 holes, donut has 1 hole, and this particular weird structure has two holes. So if you don't punch new holes, or if you don't rejoin things, but if you adiabatically deform, then there is no way you can go from a sphere to a donut to this particular structure, or backwards. So these are called, this genus is the topological invariance, and you can get the these genus values from the famous Claude-Bonnet theorem. So this is basically the topology. The idea is the different insulating states in a condensed matter system are described by different Hamiltonians, and you cannot, if the topological invariant of those insulator states are different, then you cannot adiabatically transform one insulator to the other. So this is unless you close a gap, which is called the topological phase transition regime. So what these two people realized was, instead of applying magnetic field, you don't have to apply magnetic field, but you can use certain properties of the material itself. And that, and what they realized was the spin orbit coupling. So if the spin orbit coupling of the system is large enough, then one can have what is called band inversion. So band inversion is an important aspect of topological systems. And the idea here is, in a regular, let's say, a trivial insulator, although they're by no means trivial, but from topological aspect, let's call them trivial. You have a particular ordering of the bands. For example, in cadmium sulfide, the valence band is made of p orbitals. The conduction band is, at least close to the gamma point, is made of s orbitals. And if you introduce if the material has very strong spin orbit coupling, then you can mess up the ordering. So the conduction band can actually go below the valence band, and this is band inversion. And these are defined by, again, it has to follow certain symmetry constraints and all, by other topological invariants, which are different from the regular ordered band structure. So, and these two are different insulators. So now if you create an interface between an insulator which has one topology of one topological invariant, and you join it with another insulator with another topological invariant, then at the crossing, at the physical interface, the system has to correct itself. And this can, because it goes from one to the other. And by doing so at the interface, it has to close the gap. And this led to the idea of topological insulators, where you have insulating material. Material is an insulator in the bulk, but at the interface, it could be interfaced with the vacuum, which is because vacuum is a trivial insulator. One can create these states. And the interesting, important aspect of this quantum spin Hall system is, because you don't apply any magnetic field, the time reversal symmetry is conserved. And because of which, you can think of these topological insulators as two copies of the quantum Hall system, but with different spins. So in a quantum Hall effect, you just have edge transport. But in a quantum spin Hall effect, because the total time reversal symmetry has to be maintained, so electrons with a particular spin, let's say spin up, move in one particular direction along the edge, and the other spin, electrons with the other spin, move in the opposite direction. So overall, the time reversal symmetry is maintained, but it's a new system, not requiring magnetic fields, so time reversal symmetry is maintained, and you have this spin-dependent transport. So this is the idea of topological insulators. And then there's a lot of, and then Haldane's work in, I think it's been more than 10 years now, they realized that this is more of a wave phenomena than just a quantum, that rather than only being a quantum phenomena. Electrons are waves. So can you extend these ideas to other systems like phonons and photons? And the answer is yes. So there's a lot of work. So one particular work which is relevant to ours is what I'm going to describe, and that is can we get analogous photonic, photonic analogs of quantum spin Hall effect. So there's this very famous paper, in PRL from Wu and Hu, where they showed that if you have if you have a honeycomb lattice, photonic lattice, then these are photonic orbitals. One can create these photonic orbitals in these honeycomb lattice by confining light. And this is basically the H field, out of plane H field. So one can create these orbitals, like this is the p-type equivalent orbital or the d-type equivalent orbitals. And then if you have a honeycomb, then you have a Dirac crossing. But if you can expand with keeping the same hexagonal symmetry, C6 symmetry, if you expand or contract the lattice, you break the C3 symmetry, so you gap out the system. And the two systems, the expanded or the contracted, correspond to two different photonic insulators, okay? Quote unquote photonic insulators. And if you create an interface between these two systems, then you can have edge dependent, photon spin dependent transport at the edges. And again, one can ask, the quantum spin Hall effect they describe is for fermions, electrons, and these are photons. So these are all, so what time reversal symmetry are we talking about? So the idea is these are pseudo time reversal symmetries. By combining the time reversal symmetry of the Maxwell's equation and the crystal, and the symmetry of the crystals, one can create these time reversal, pseudo time reversal operators which follow, t squared equals to -1. Hence time reversal symmetry is maintained. So this was the idea, and then a few years back, Mohammad Hafezi's group came up with a better experimental realization of this system, and they realized instead of making these circular holes where you cannot create a very nice band gap and light is not very nicely confined, is to make these triangular holes, but following the honeycomb symmetry. One can get one can realize these things in the photonics regime. So since we wanted to create polaritons, we knew, and there was no work prior to us, that we had to push this quantum spin Hall effect in the optical regime, which means visible light, 500-600 nanometer regime, which is hard, not in terms of concepts, because these concepts are already derived, but from a fabrication perspective. So yeah, so again, once you start with this hexagonal lattice, this is the regular honeycomb structure with a Dirac cone. So you can create, we can expand the lattice or contract the lattice. This basically, if you're aware of this Su-Schrieffer-Hugo model, so all this expansion and contracting the lattice basically leads to different inter and intra-cell hopping rates. So like in an SSH model, by playing with this intra and inter-cell hopping, one can create different insulators with different topologies. The idea is the same, pretty much, except it has this 6C6 symmetry. And the idea is when you expand or contract the lattice, you break the C3 symmetry of the system, and hence you gap out the system. Okay, so this is pretty much the idea, and you can, so important thing to note here is, as I said, these are all tight binding calculations of the photonic structure. So when you have the regular T1 equal to T2 honeycomb lattice with C6 and C3 symmetries, you have this Dirac dispersion. But if you have this T1 greater than T2, then you have a conventional photonic insulator. And as you can see, this valence band, quote unquote valence band, has a dipolar p orbital structure, and the conduction band has the d orbital type structure. And in the opposite regime, when you expand the lattice, it's reversed. So now you have a p type orbital structure in the conduction band and the d type in the valence band. So these two are, compared to this is inverted. And if we create an interface between these two structures, at the interface, one can have these quantum spin Hall, topologically protected modes. So we fabricated these structures using silicon nitride and did case momentum space spectroscopy. So this is in the trivial regime. So this is the p band. So this is a dipolar structure. It couples to the far field. So that's why it looks bright. Here you can't see it, but there's a dark mode corresponding to the d orbital picture. And in the inverted regime, you can see it's reversed. So this is d orbital. That's why it's dark at this gamma point. And here it is. It is bright. So it's an inverted structure. And when we when we create an interface between these two photonic structures, there's a mode here, and photons can only propagate along this zigzag mode. So if at the interface, if you do K-space spectroscopy, we see both the spin-dependent modes. This is so linearly polarized light excites both right and circularly polarized photons. So one propagates. You can see it has a positive slope. So in one direction, the other has a negative slope, so it propagates in the other direction. But if you shine with only right circularly polarized or left circularly polarized light, you can see only one of the two modes are selectively excited. So we have propagation in one direction or the other direction, depending on the polarization of light. So this is more striking example of this. So we shine different colored lights. These are different photonic structures because one has to be in resonance. But this can only happen in the band gap regime, where we create this photonic gap. So linearly polarized light, we have transport in both directions, and then one or the other, right or left circularly polarized, basically transports the photons in different directions. So this was in the photonic regime. Photons are very interesting, and the fact that you can do this is interesting. But you can't tune the properties of photons that much. The refractive index of the medium doesn't change much with temperature. Photons don't care about fields, and this is why this community is very actively working in polaritons, because via these material excitations, one can create very large nonlinearities in the system. And also because of the excitons or other materials excitations, these excitations respond to the external fields. So can we create topological polaritons? So the breakthrough happened in 2 or 3 years back, where people showed in a hexagonal lattice of these Bose-Einstein condensates, one can create a quantum Hall analog of these structures. So since these are Bose-Einstein condensates, and the band gap is opened by applying a very strong magnetic field around 5 Tesla, and the gap is very small. So this phenomenon of quantum Hall analog of polaritons was demonstrated at very low temperatures, but nevertheless, it was a big breakthrough in the field. So we started to think, can we kind of push this? Can we create topological polaritons at room temperature, or close to room temperature? And can we, if we have a quantum spin Hall analog of these polaritons, then we don't need to apply a magnetic field. Okay, so this was the idea. So this is step one that we've taken. So the idea is, if we start with a topologically non-trivial photonic structure, the photonic structure that I described, and then if we basically integrate this with a two-dimensional materials, so that it interacts strongly with the optical field that we create, then what will happen? So let's say this is the dispersion that I talked about, just the photonic dispersion. Now you hybridize this with the exciton. Do we have a trivial opening of the band gap, or can this interaction lead to a certain topological aspect in the system? Okay, and it's not clear. It was not clear. What would happen? So we had to do a lot of calculations, develop I would not say fundamentally new theory, but protocols that work for us for this polaritonic system. So one thing was very clear, and that is, at least in this regime where we have a photonic crystal, which is topologically non-trivial, we have to have excitons which basically follow the symmetry of the system, and they should be isotropic in terms of their polarization properties. So so these red particles are excitons or photons, and then we basically have we assume a homogeneous distribution of excitons. So at each cell that we define, unit cell that we define, we have an exciton and a photon following the same symmetry properties of the underlying lattice. So the excitonic material, at least in our step one, first demonstration, does not break any of the symmetries. So we write the tight binding Hamiltonian for this strongly coupled exciton photonic system. We hybridize it, and then under the two regimes where you have the trivial regime or the non-trivial regime, we calculated the band structure. So these are the three-dimensional band structures. And interestingly, by tuning a lot of parameters, we were able to find the regime where there is actually band inversion of these polaritons, okay, of this coupled polaritonic system. Okay, so you can see here it is blue, here it is red, in the other regime, and vice versa in the conduction band. So this got us excited, that indeed we can get topological polaritons in the system. Okay, so these are more calculations to show that as a function of these lattice parameters, one can invert the system. So So we have, if the valence band has odd parity, this is in a regular system, and by changing the lattice parameters, these calculations show that indeed we can invert, and then in this regime, the 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 valence band can have d-type orbital characteristics in the polaritonic regime. This is not the photonic regime, and when we create an interface between the two polaritonic lattices, so this is the interface. So we solve the interface mode equation. So on one side you have there's this mass of the system which has a particular sign plus, and the other side the mass has a minus sign, and this transition takes place at this interface, and this is where the interface topological interface mode can survive, cannot decay into these two bulk structures. So interestingly, in this polaritonic regime, what happens is when the system is topologically non-trivial, a Dirac cone basically splits, a photonic Dirac cone basically splits into two Dirac cones, as you can see here. And this, has everything to do with the light matter coupling strength. And interestingly, we can solve the bulk and put the same coupling and obtain the coupling strength of the system. And at the interface modes, the splitting of these two Dirac cones is a function of this light matter coupling strength. So it basically, roughly speaking, one can say this is sort of observation of the bulk edge correspondence. And this calculation also shows, and we've done experiments to show that indeed the light matter coupling strength, the square root of the oscillator strength, the splitting between the two Dirac cones can be tuned. So the stronger the coupling strength, more splitting of the two Dirac cones. And these are the two polaritonic interface states. And FTDT simulations also reproduce these results, so everything checks out. So here's the experiment. So this is what you see here is the underlying photonic crystal. On top of it, there's WS2. This is one type of lattice. This is the other type of lattice. These yellow zigzag lines shows the interface mode. So momentum space spectroscopy, basically, one can map out these modes. These are the two Dirac cones. This is, there are a lot of bands here, and there's a bulk gap here. And these bands themselves have very interesting properties, which we are trying to explore now. And polarized reflectance spectroscopy, shows what was expected, thankfully. These are the bulk bands, and the interface modes, basically in the reflectance spectroscopy also shows these circular polarization dependent modes. So left circularly polarized light lights up one particular interface mode. These are topological polaritonic modes. And then the other circular polarization lights up the other interface mode. And then these can be tuned with temperature. And if you measure the photoluminescence of these structures, so if we excite, these materials emit light. So this produces an incoherent mixture of emission. And if we create the band gap of this polaritonic mode in the emission regime of this WS2, then right circularly polarized light kicks off the polaritons in one direction, and the left circularly polarized light kicks off the polaritons in the exact opposite direction. We can measure the dispersion of these of this photo emission. Again, we can see very nicely these bulk modes, and one particular circular polarization, only one particular channel lights up in the K-space dispersion, and the other lights up the other. Since these are topological polaritons, idea is can they navigate a very sharp turn without backscattering? So clearly they're not backscattering, one can see, but can they also navigate a very sharp turn? So we basically created the zigzag interface mode with a very sharp turn, 120-degree turn, and clearly they can navigate this turn without backscattering at this point. And these are polaritons, these are not photons. So all these things are very interesting, as you can imagine, because what we've created are these polaritons with spin-dependent properties and a protection from backscattering. So the loss mechanism further decreases. So we've not done electric field tuning yet, which is something we're trying now. And I mean, in principle, it should work. But temperature dependent tune.
Sorry, we had one question here.
Yep.
Hi, I have a question about your previous slide. So in the PL experiments, do you just excite with circular polarized light, or do you also observe the circular polarization of the emitted light?
No, this is circularly polarized light excitation. Yeah.
if you looked at the polarization of the emitted light, would you see that the polarization is the same as the excitation?
Yeah, it's a
polarization,
great
or-
question. I don't have that slide, but I didn't, oh, I don't have that slide, but you're exactly right. That by which we measure the rate of depolarization because of other scattering effects. So so if you check our paper, I have this older version. So there is another panel where we showed exactly what you're saying. And then from that, we track how much is this emission getting depolarized. And if you account for, if you remove all the other effects, the depolarization is actually quite slow or quite weak. So you're exactly right.
Okay,
So if
thank you.
yeah. A great question. So yeah, so temperature dependent tuning of these polaritons showed that in the temperature range, that we tuned, the topological properties remained intact, which was very good, very promising that we didn't destroy the topological properties, and the group velocity could be tuned to very, to by orders of magnitude within 10 or 20 degrees. So that's really promising, as you can imagine, for tunable topological polaritonic devices. If in 10 or 20 degrees, how much a photonics mode responds to? Pretty much nothing. And we've done experiments where it shows nothing measurable, no measurable change. But if you have a topological polaritonic system, we can control a lot of property, very significantly the properties of these polaritons. And again, in the device context, this is, we want to integrate this field effect transistor type geometry in our topological structures and electrically tune these properties. So that's a work in progress. Since I'm running out of time, so our next step is, can we combine two topological polaritonic channels and make them interact and see, once you have two interacting topological channels, of course, you won't have a zero mode topological mode, but can still some of the effects that come from mode isolation in this band gap be translated, and can we do something more interesting? So we've taken the first step and shown in the photonic regime, indeed, if you have two different topological modes, photonic modes, and we are extending this to polaritonic regime, these two topological channels interact, but as long as the mode of the two modes are in the band gap, photonic band gap regime, one can confine excitations only in these topological modes, and and backscattering is less. It's not zero because, of course, it's not purely topological, but still, it's, there is no mode to scatter to. There are no modes here, so that is why backscattering is strongly suppressed, and we've used this to make topological logic gates. But in the photonic regime, and the idea is to extend this to polaritonic regime. So I want to end my talk with the vision that we have, of utilizing all these things and the other activities in my group to create a chiral integrated nanophotonics infrastructure. And the motivation is from, from spintronics, our electronic devices and also photonic devices, even as of now, electronic devices, in spite of the advances, still work by counting the number of electrons that flow in the circuit. These transistors turn on and off, and you just measure the total current that flows in the circuit. And that's the distinguishing factor. You can have multi-level systems, but information is only encoded in the amount of current that flows in the circuit. Okay, and the idea of spintronics is, can we also utilize the quantum spin degree of freedom of electrons or charges to encode more information, to send and transduce more information? So we know the state of this field, so it's very promising. So can we do the same thing for photonics? All photonic circuits right now are also working along the same idea that you measure just the light. When you have a modulator, you just measure light on and off. But photons also have spin degree of freedom. And in addition to spin degree of freedom, they have an extrinsic degree of freedom, which is the orbital angular momentum modes. These are the spatial modes of light. So can we encode more information in the photonic structures? So people have been working on this for some time now, but to create these chiral photons with orbital angular momentum, to route them and to detect them requires a room full of optics, bulky optics. So can we miniaturize this on a small chip? And it's a very difficult problem, and it's a very interesting physics and chemistry problem. And my background in spectroscopy helps a lot here. So we need an on-chip generation of photons with all these chiral and OM degrees of freedom, routing of these, which is what I talked about. These topological photonic and polaritonic routers, and detectors, on-chip detectors, which can detect this chirality and these orbital angular momentum modes. So this is many years of work in the last, put together in one slide. So we have taken first very promising steps towards all the three directions: generation, transport, spin-dependent transport, and detection of these OM and chiral degrees of freedom. So working with, this is spearheaded by my colleague in my department, Liang Feng, recently showed that, indeed one can make on-chip OM and chiral photon laser sources, and one can basically make a tunable source where we can change the OM and the spin degree of freedom of light that is emitted. This is what I've, the transport part is what I focused about in my talk. So not OM yet, and I don't know how to do OM transport, dependent transport, but we'll see how it goes. But at least for photon spin degree of freedom dependent transport and polaritonic transport is what we demonstrated. And this is some very interesting work from Zurun G in my group, who showed that by coupling wild semimetals, which are topological semimetals, and endowing them with some external spatial geometrically designed electrodes, one can indeed measure the OM, the different OM modes of light on chip. And this indeed is a breakthrough, because we use principles of non-local optical spectroscopy. These interactions cannot be described by electric dipole type interactions. So these are quadrupolar or magnetic dipole type interactions. But by engineering these interactions, one can detect indeed on chip direct readout of this OM mode of light, and of course spin angular momentum of the photon. So with this, I'd like to end my talk.
Sorry.
Yeah, and
we did have one more question, yeah, towards the end here.
Yeah, I'm pretty much done. So the idea is, if you understand how light interacts with matter and these complex geometries and complex materials, one can then push the limits and create systems that that are very interesting and give us new platforms to play with. So I'd like to thank you all for your attention, and I once again thank my group members and the funding agencies for supporting this work. Thank you.
Yeah, thank you very much, Professor. That was an excellent talk. I see that there's a few questions here towards the end. If you had some time to go through them,
yeah, sure.
I'm sure everyone would be very eager to hear.
Hi, I have very nice talk. I have a few questions. So your excitons in the MOS2 are isotropically oriented in the 2D plane. So I suspect that here the magic is that you don't have dipoles pointing along the z direction out of plane. I guess could you comment if you had these excitons out of plane, would any of these things work? Like, for example, if I just put like an isotropic blend of some organic molecules or something, I believe that then this very nice matching of the symmetries of the photon modes and the symmetries of the exciton modes would not hold anymore. Is that correct?
It depends. It would depend on the nature of interaction in the z directions. So if you have, as you correctly pointed out, if we had like a multi-layer, like 8 or 10 layer stack, that's when the z direction dipole starts to build its oscillator strength. So it would depend on how strong that particular orientation interacts with the field. So I know
you wouldn't have this very nice separation of sigma plus and sigma minus sectors of the Hamiltonian, if I understand correctly. If
the coupling is strong, yeah, it will interfere, of course. But if the coupling is strong, it will interfere, as you rightly said, it will interfere with that with that separation. Yes.
So right. Maybe another way to put it is: are the photonic modes that you are engineering, do they have the ability to couple to dipoles in the z direction, or for some reason these things only have polar electric fields along the xy plane?
So right now it is indeed true, because the magnetic field points in the z direction. So you have very strong in-plane transverse field which couples to these excitonic dipoles. So
wait, but then you have TE and TM modes in each of these pillars, right? So like you should always have like the z direction electric field. Or am I not Correct.
So the field, the magnetic field is in the z direction right now in this regime of look at these are membranes. So these are very thin membranes. So that is why the electric field, the transverse electric field, is very strong in the x or y, in plane direction.
Okay, I see.
Yeah.
So there is little electric field in the z direction.
I mean, it probably is there, but it's very weak. Yeah.
Okay.
But I think if you change the thickness of these membranes, then you can start creating the fields in the z direction also. So that's why we had to work with the suspended membranes, not on a substrate.
Okay, and I have other questions, but maybe the most pressing one here would be the C6 symmetry that endows your system with topological properties. I mean, clearly, when you create edges, you break C6 symmetry. Can you comment why you still have this topologically protected behavior?
Yep.
I'm sure that has been discussed somewhere, but I don't know the answer for this.
Great question, and you're exactly right, because although the bulks are fine, because they maintain their symmetry, but the interface breaks that C6 symmetry. So indeed, a very small gap is created in the bulk, but that is of the order of few MeVs compared to other energy scales of the system. So very strictly, if you look at it, it does gap out the system, but that gapping is within this engineering error. So even the original authors of the paper, this PRL paper, Wu and Hu, pointed this out, and they also said, as long as the resonances are not that narrow and you're not resolving on that length, on that energy scale, it should work, and indeed it works.
Okay. Thank you very much.
It's a great question, though.
So we have, oh, sorry, if there was
Hi.
time, we had a few more questions. Yeah.
Hey, nice talk. So I just want to confirm that, do you have a large single crystal WS2 to cover the your photonic crystal system?
That's right. I mean, again, what does large mean? So of the order of, few 20 or 30 microns. So enough interaction can be engineered in these structures. Yeah.
I see. And how about the relative orientation between the two-dimensional semiconductor and the photonic crystal? Does that matter?
Not as long as we have isotropic excitons.
Okay, I see.
Yeah.
All right, thank you.
But since these questions have been raised, so we, if again, as I said, this is just the first generation device. One can also engineer polarization dependent responses and also take the system through very different insulating regimes through a phase transition via these polarization dependent responses. So that would probably be the next step, to couple these two systems with anisotropic polarization of excitons, and then engineer these effects.
Mm-hmm.
Okay. So if you had a moment, we have a couple more questions.
Hey, can you hear me?
Yeah.
Hi, Ritesh, David Masiello from Seattle. This is my first Polariton meeting, so also thanks to the organizers, Joel and company in San Diego. I had a technical question for you. Well, first, I really enjoyed your talk. Technical question had to do with the spatial variation of the lattice field, both for the square lattices and the hexagonal lattices. You showed an illustration, a calculation, I think earlier on, that really showed strong inhomogeneity of the diffractive lattice modes. And as you add polaritons into that field, I'd imagine there's a variety of coupling strengths that are spatially dependent. So you might have populations of, populations of emitters that are weakly coupled all the way into strongly coupled polaritons in other regions. And I'm wondering if you have any experimental ways to probe the inhomogeneity of the coupling strength. I saw at the end in the type binding models you were writing down, you just had a single constant valued G. But again, technical question, just curious to hear your thoughts.
So, I mean, so you're exactly right. So right now, this is all, whatever line width you have, you just, it's a single parameter model. But what you say, I mean, we've not done this, of course, not yet, but it's a very interesting question. And this also leads to, okay, so one is an artifact and, it's an engineering, thing. So one can try to minimize, but of course there is spatial dispersion of all these properties. And this, this leads to, mostly it leads to this reduction of this coherence coherence of this interaction length scale. So it makes it smaller. And if it is homogeneous, then the level repulsion will increase. But this also can lead to, if it can be engineered, and we have some thoughts, if it can be engineered, then this can lead to very interesting spatial dispersion effects. And the example that I showed of this many layered systems interacting with the plasmonic lattice actually utilizes this spatial variation of this interaction. So so this spatial dispersion is actually a very important point. So right now it's just treated phenomenologically, but what you raise is a very interesting and important aspect. And if it can be engineered, it can lead to more interesting
absolutely
of the system.
Yeah, I completely agree. Hey, thanks, Ritesh. Thank you.
So I think this will conclude this week's webinar. I would like to thank Professor Agarwal once again for the excellent speech here. I think you guys can see this here. Yeah, very interesting and much appreciated. And I wanted to announce before we wrap up here, next week's webinar on March the 24th will feature Professor Sang-Hyun Oh from the University of Minnesota. Be sure to register in advance to participate in that. And you can check out the recording for this week's webinar on YouTube, and be sure to keep up on everything and continue the discussion on our Facebook and other social media platforms. So with that, I'd like to ask everybody again to thank Professor Agarwal for the great talk, and we will.
Thank you for the invitation.
Yeah, thank you so much. We will see you all hopefully next week. Thank you.
Thank you. Bye.